So let's pick up where we left off on this. So we're looking at a limit like this one here. I'm not going to redo this one, but it's a good one to talk about. Okay? And I cannot evaluate this limit through direct substitution. Okay? I can't even apply the quotient rule for limits to this one because the limit of the denominator would come out to be 0. More often than not, if you look at a limit question, it'll meet those conditions, right? Those are the tough ones. If the limit involves direct substitution, it's not too much work. We're not going to ask more than 1 or 2 of those because we realize, okay, we got it. Okay. The ones that require work are the ones where you can't use direct substitution and the quotient property doesn't apply, and so you have to do some sort of trick to make it easier to work with. Okay. This was a mean one. Okay. Absolutely, each one of these that requires a special trick, work through them a few times until you learn to recognize what that trick is, when you should apply it, etc. Okay. Eventually, what happens? Well, by working, and in all these problems, I'm working inside of the limit. I still haven't evaluated the limit, right? I'm cleaning it up, cleaning it up, cleaning it up. Then I'll apply direct substitution. That's how the procedure basically goes. Okay? And notice that it is this x squared factor in the denominator here that's preventing us from using the quotient property and eventually direct substitution. But by the end of it, we have canceled out that factor that was giving us fits. Okay? So keep that in mind as your general strategy. Eventually, you want to be canceling out the thing that's preventing you from using the quotient property or direct substitution. Okay? All right. We then looked at doing left and right hand limits. And there's not a whole lot of examples where we do these left and right hand limits where they're interesting, where you get something different than if you just done the limit proper. So a classic example of where it's useful to use left and right hand limits is when the absolute value function appears. Okay? And I would definitely work through this example a few more times. Okay? Doing it once was maybe a little tough. Maybe it made sense in class, but I don't think you've got it until you've worked it a few more times. Okay? Just take your notes, write out the question on a blank sheet of paper, and rework it 2 or 3 times until you got it. Okay? All right. So let's do a couple more left and right hand limits. Okay? So we're going to analyze this one analytically first, and then we'll just return to the graph and say, oh yeah, I see that. Okay? So I'm looking at the limit as x approaches 3 from the right of this square root function. Okay? So here we go. This is the limit as x approaches 3 from the right of the square root of x minus 3. Now, what would I like to do? I'd like to get to the point where I can use direct substitution, right? We said we can do direct substitution if we got it down to a polynomial, right? Yeah. Or a rational function where it's defined there. But I notice I do have a polynomial inside the square root, but the limit is where?
It's outside.
Outside. So what would you like to do?
Put the limit inside the square root.
Yeah, we'd like to be able to pass the limit through the square root, right? Can I pass a limit through an nth root? Yes, but remember there was the asterisk there, right? Provided the domain values around which we're evaluating the limit are all positive if it's a square root, if it's an even-ordered root. Okay. So let's just look down the road just a little bit. We're plugging in numbers like 3.1. When I subtract 3 from 3.1, I've got a very small but what sign number? Positive. So I can pass this limit through this square root. Okay. So I'll go ahead and do so. But remember, if I stop to talk about a move for a few minutes, it means there's something subtle going on there. Okay? All right. So we pass the limit through the square root. Okay. But now what are we taking the limit of? x minus 3, which is a polynomial, right? So we can recklessly, with polynomials, be as careless as you want. Okay? With polynomials, we can now evaluate the limit through direct substitution. So here we go. This is just the square root of 3 minus 3,
0.
which gives us the square root of 0, which is 0. Okay? Here I'm approaching the limit, or here we're approaching 3 from the left. One way to look at it is we're plugging in numbers for x like 2.9, 2.99. When I subtract 3 from that, what type of number do I get underneath the radical? Negative. Can I evaluate those? No. So remember, the definition of the limit, if you go back to where I defined it, I said let the function be defined around the value that you're taking the limit. But right now we're taking the limit at a boundary point for the domain. So I can't approach it from the left. So the question, what is the limit, as I approach from the left, doesn't even make sense. Okay? So this limit does not exist. Okay? Again, one way to look at that is I can't pass this limit through the square root because the values to the left of, when we plug in numbers to the left of 3, would give us a negative underneath that square root. Okay, so I can't apply the square root property in case B. Okay? So let's just say since, well, yeah, I've said so. So yeah, we'll leave it at that. So then what's the limit proper?
Does not exist.
Does not exist. Sort of for a different reason. I couldn't do this one because I couldn't approach it from this direction. But once I say the left-hand limit doesn't exist, then the right-hand limit, or sorry, then the limit proper can't exist. Okay. How are we doing? Okay, give me a thumbs up, thumbs down, thumbs sideways. Awesome. Sideways is okay. Okay, sideways is definitely okay, but it means you gotta before next time we gotta get it up to a yes, I feel certain about this. Okay? So just put a note there, put a star, work on it a couple more times on your own if you have time, or come by and see me and we'll talk more about it. Okay? So if you're sideways on something, that's okay. But you got to get it corrected before next time. Okay? All right. I'm going to skip number 16. Okay, it's an interesting question, but I want to skip through it. Maybe if I get a chance, I'll put a video up for it. All right. This next theorem tells us that if I know that one function always sits below another function, then I can make a statement about their limits, provided their limits exist. Okay? So first of all, I use this symbol here. I'm sort of regretting doing so. This is the symbol for all. You're going to see it in further math classes. Okay? It's just a shorthand. Okay? So suppose the y values of f are at or below the y values of g for all x in the domain. Okay? Except at possibly a itself, which is where we're evaluating the limit. Okay? Now here's this, I'm going to talk about limits in just a second, so they better exist. Okay? So if f is always below g, then if the limits exist, the limit as x approaches a of f of x must be less than or equal to the limit as x approaches a of g of x. And the picture that goes with this is if I have some function g of x here, and I have some function f of x here, what do we notice? We notice that the y values of f are always below the y values of g. Okay? That means that if both these have limits that exist at a, this L value must be below this L value. That's all we're saying there. Okay? It's not too exciting of a theorem, but we're going to need it for the next one. Okay? Oh, questions on that? This is kind of a stepping stone for the next theorem. Okay? So the next theorem is a big one. It's a very important theorem in math. It's called the Squeeze Theorem. Sometimes it's called the Sandwich Theorem. Okay. And it says, suppose you have a sequence of three functions. One is always less than the other, which is less than or equal to the other. Okay? So suppose f of x is less than or equal to g of x, which is less than or equal to h of x. Okay. If the limit as x approaches a of f of x equals L, and the limit as x approaches a of h of x equals L, so I'm saying as we approach a for f, our y values are getting close to L, and as we approach a for h, our y values are getting close to L. What do we know about the function that's trapped in between them?
It has to be L.
Its y values also have to be approaching L. So then the limit as x approaches a of g of x must equal L. Okay? There's actually two parts to me writing that. First, we would say the limit exists. And that's the case. Because remember, limits don't always have to exist, right? But if the one above it has a limit exists and the one below it has a limit that exists and they're the same, then it must be trapped between them. Okay? So here's the picture that I think goes with this. Okay? It's a good picture to keep in mind. Let's see here. It's always a little tricky for me. H of x was the function that was greatest for a while. F of x, which was the function that was least for a while. And then here's our g of x. Okay? So this is in practicality how we use the Squeeze Theorem. Suppose yellow is a really, really messy function. It's hard to work with. I'm trying to evaluate a limit with yellow, and I can't. Okay? Well, if I can show that yellow is trapped between blue and red, always, over some interval. So notice it's not always between blue and red, but there's some interval starting about here where yellow, oops, not quite there, right about here, where yellow is always trapped between blue and red in that interval. Okay. Then since here we see the limit as x approaches a of the lesser function, which we're calling f of x, that must equal L, and the limit as x approaches a of g of x must equal L, then so must the limit as x approaches a of g of x. It must be L as well, even though I can't do the work to see it. Yeah, Sean.
The middle one needs to be H of x.
Thank you. Thank you. Good catch. Good catch. Okay. So again, if I can easily work with h of x, and I can easily work with f of x, let's use colors. If I can easily work with blue, and I can easily work with red, then even though yellow is hard to work with, I can still make a statement about its limit if this is a very important condition, is met. Okay? All right. So let's see an example of using this Squeeze Theorem. Okay? It's also sometimes called the Sandwich Theorem. So let me first back up just a little bit. We saw the function, the sine of pi over x, early on in this course. I showed you this function. Remember what it looked like? Its graph looks something like this. Here was 1, here was minus 1, and it went something like this. Remember that one? Okay. Well, it turns out that that would work also even if this was just 1 over x. They're really the same. I mean, the graph is very similar. The only difference is exactly which points it's passing through. Okay. So it turns out that the limit as x approaches 0 of the sine of 1 over x does not exist. We said that last time. It was our very first example of a function whose limit didn't exist at a place. Okay? Well, this is really interesting, because here this function shows up again here, right? Okay. We're going to see that we can actually find the limit for this function. Okay, this is where functions don't behave as you would necessarily expect them to. Okay, so let me show you the wrong way to do this problem. Okay? The wrong way to do this problem is to say, hey, I've got this product of two functions here, right? The wrong way to do this problem is to say, hey, I've got a product of two functions, and he said before, the limit of the product was the product of the limits, right? He said before that you could distribute a limit over a product. What would this limit be?
0.
So this is 0 times whatever this comes out to be. So we get 0. Okay, there's two mistakes in this problem. First of all, 0 times a limit that does not exist, we don't necessarily know what that's going to become. Okay, so that's the first mistake. Okay, but that's not the one I want to highlight. There was another mistake here. Made a mistake right off the bat. What was the first thing I did? Distribute a limit. Can I distribute a limit over products? That's what. If you turn a page, it says for a product though. So that was, you're thinking of the quotient rule, I think. Yep, that's all right. Will?
Was it sine 1 over 0?
No, because you can't evaluate it at 0, right? So if you go back to the limit properties that start at 2.3, I mean, you'll see that we wrote down the limit of the product is the product of the limits. But all of these properties had a caveat to them. What was it?
The limit has to exist.
You can only use any of those properties provided the underlying limits exist. Okay? So you cannot do this because you can't plot. You can't. Forget this silly argument here. The real issue is you can't distribute the limits over multiplication in this case. Okay. So in all actuality, when you try to use your limit properties, what you do is maybe you apply the property first and then later find out that you shouldn't have been allowed to do the property and you backtrack. Okay?
So how do you find that out if it just equals it?
Yeah. How are we going to find this limit? Okay. How are we going to do this limit?
Sandwich.
Yeah. The theorem we gave just before it. The Squeeze Theorem. Right? We've got a really, really messy function. Let's see if we can trap it in between two functions and then come up with its limit. Okay? So this is our technique. Okay? I need to start with a fact that we can all agree on, and then I'll build it from there. So I think the fact that we can all agree on is that the sign of an expression always jumps between -1 and 1, right? The output of the sine function is always between -1 and 1. Everyone okay with that? It doesn't matter what expression's in the sign, provided the sign's defined there, you can do so. You could say that the amplitude's found between -1 and 1. Okay? The only time this fails is where it's undefined. It's undefined at 0, but are we ever plugging 0 into this problem? No, this is absolutely essential that you understand with limits. We don't plug the number into the function. We examine the behavior around that number. Okay. So if I can get you to all agree on this, we can keep going. Okay. My goal is to build this function right here that I'm working with. So what does it have on it? x squared. Let's multiply all three terms of this by x squared. So this gives us x squared is less than or equal to x squared sine of 1 over x, which is less than or equal to x squared. Oops, this would be what? Oof.
Negative.
Oh, 23rd mistake. It's not even 10:30. Questions on that? Well, so do you see how we're starting to satisfy the conditions for the squeeze theorem? We first showed that our messy function is trapped in between minus x squared and x squared. Okay. So now let's look at the limit as x approaches 0 of the two endpoints. Okay, so here we go. We say the limit as x approaches 0 of minus x squared must be less than or equal to the limit as x approaches 0 of x squared sine of 1 over x. Must be less than or equal to the limit as x approaches 0 of x squared by the squeeze theorem provided the two end limits exist. Okay. So I have to show that this limit exists and this limit exists. And I guess I should add and agree. I'm sorry, I want to change the way I'm writing this, folks. I don't like the way I did this. I'm going to erase this on you. Okay. I don't like the way I said that. 24. All right. So let's just look at the limit as x approaches 0 of minus x squared. What does that give us?
0.
0. We can apply it.
0.
Well, yeah. So if we apply direct substitution, we get negative 0 or 0, right? And if we look at the limit as x approaches 0 of positive x squared, what do we get?
0.
0 squared, or 0. Okay. So now we can go ahead and apply the squeeze theorem. By the squeeze theorem, we have that the limit as x approaches 0 of the middle function must also equal 0. Will, there was a question.
Yeah, so just to recap why the squeeze theorem works there, it's because the sine function outputs something with a magnitude between 0 and 1.
Between negative 1, well, magnitude, yes, sure. Yeah.
So multiplying by that will never take you outside the bounds of the x squared function or negative x squared?
Well,
like, is that why?
no. So there is no. The actual issue is there's a property of inequalities that says suppose A is less than B. If C is a positive number, then AC is still less than BC. Okay. And so I was multiplying both sides by x squared, so it's always positive unless x is 0, but we're not plugging in 0, so we're approaching 0. Yeah. Great. Sean.
You said before about the squeeze theorem, so it's basically the function f of x is essentially negative 0, and the function h of x is essentially 0, so it's squeezed between negative 0 and 0.
So let's be careful here. The function f of x was minus x squared, and the function h of x was x squared. The limit of f of x was 0 as we approached 0, and the limit of h of x was 0 as we approached 0. Therefore, the limit of the middle function must exist and be 0. Yeah. Great. Folks, one thing I encourage you to do is to try to talk math aloud. Okay? If you've got a little brother, a little sister, a niece, nephew, a child of your own, teach them calculus this semester. They won't learn it. They won't learn it. But if you teach them calculus this semester, if you teach them that, you'll learn a whole lot by trying to verbalize these things. Okay? So I really encourage you to come by and just talk math with me, or talk math with your study group. Okay? Because that's where, as one of us corrects the other, that's where you begin to really pick up on it. Okay? Yeah. Yeah. That was a good question. All right. Let's look at the graph of what's going on here, just so we can kind of see. So we just analyzed this without the graph. Okay. So it turns out that the sine, it turns out that x squared sine of 1 over x, its graph looks like this. Okay, let me go down just a little further. Okay. And we'll go down a little further. I didn't do the best of jobs of graphing this, okay? But the graph of this function, let's undo that. Yeah, let's just undo that. Let's try it again. So, folks, I can't draw it without first putting in the asymptotes. I'm not good enough. So let's put in the asymptotes here. This has what are called quadratic asymptotes. And the graph of this function looks like this. Last part's a little off. The green graph is the graph of x squared sine of 1 over x. Notice, just like sine of 1 over x, it exhibits this extremely rapid oscillation. And the limit as x approaches 0, the sine of 1 over x did not exist. Why? Because it was oscillating between which two numbers? 1. Okay. What does this end up oscillating in between as it's oscillating at its most rapid? 0. Between 0 and 0. It's trapped. That's why the limit as x approaches 0 of x squared sine of 1 over x is 0. Yeah, Marissa.
So the outer functions that we use, the negative x squared and x squared, basically we're graphing the asymptotes. Is that always the case?
No, not necessarily. That's I guess if you knew that a function had asymptotes, that might be a good, and it stayed within the bounds of those asymptotes, that might be a good guess. If I were sitting in your shoes right now, I'd be saying, how on earth would I be expected to do this problem on my own? And the answer is I wouldn't expect you to do this one on your own. Rather, I will show you how to do one of them and then give you a very, very similar problem if I wanted to test on it. Okay? So tackling this limit requires intuition. How do you get intuition? By somebody showing you the answer before. In reality, I mean, some people are really brilliant. They can answer these questions on their own. I can't. I saw this example in a book. It's these examples get repeated, but it's not something I would expect you to do. Okay? Why did I choose this way of developing it? Just because I needed you guys to agree with this statement. Okay? And this is the easiest way for me to get you to agree with that statement. Okay? So this is one of those problems where if I want to ask you a problem like this, I got to give you a pretty. I can't make it completely different, a completely new problem. It's got to look something like what we've done before to give you a clue that you should be using the Squeeze Theorem on it. Yeah. Great. Okay. I think that finishes out this section. Yes, it does. Great. Finally.